I am looking at one of the derivations of GBM, and uh, we start with the geometrical Brownian motion and we want to solve that equation. Now this equation becomes tricky and convoluted because we have this dw, which is a new term which we cannot integrate directly. So if we look at dw, it's a source of uncertainty, but if we can convert that into a certain number based on the distribution which we already know, that if it's a normally distributed number or so on and so forth, because WT is a process that wiggles up and down in a random way, which will change with time. So this is a Wiener process. If we can convert and get rid of this dw and get an equation that is just based out of deterministic things, so that we can use simple calculus. So to do that, there is a solution that is given in Hull's option, future and derivative books, which is the original Black-Scholes paper. It says that the solution of this GBM could be written as dv is equal to mu s dv by ds dv by dt half sigma square s square d square v by ds square dt sigma s dv by ds times dw. This is one of the way, but you see dw here. So the whole idea in the final equation that we want to get, if I may scroll up to the final solution, it would come out to be something like this, which is a partial differential equation. Here there is no dw. So in very simple words, what we are trying to do is we are starting with an equation which has this dw, which is a different way to integrate things. We cannot just integrate it right away, and finally we get with something that is not dw, which then we can use the normal calculus that we know. So let me scroll down. He says that first we start with considering a certain portfolio called delta H portfolio, and we say that it's consisting of one short position dv by ds, and the value of this holding is this new symbol is equal to minus v plus dv by ds s. Now over a short period of time the profit would change, and it would be this delta 2w and dv by ds. Now we have this equation of a stock price that keeps on moving up, and it has mu st sigma s delta dw. Then we have delta v is equal to this long equation. If we can put this whole equation which we got from delta 2, and we can substitute it in delta 1, we will observe that delta w vanishes. So if we put this here on the top, because or if we take dv by ds, we will find out that this thing would vanish, and when we equate the two formulas from the same delta H, which is this equation and this equation, both of the sides would have this term which I am pointing out through mouse, and that would vanish, and we'll get the final equation that is devoid, or which does not have the dw equation. So once we do that, it is very easy to solve this, because now we know how to solve it, because it's a normal partial differential equation. We can take everything on the left and right and solve this. So that is one way to solve the equation of Brownian motion to find out and use the property. So we say that v, which is if you observe v is a payoff function which is based up of s and t, and we defined v as this one, which is the outcome, and then we differentiated it, and then we equated that with both sides. So v is the outcome of a simple delta H portfolio, when we want to calculate dv by ds, which is the price of this with respect to change in stock price at a particular time. So the whole idea was to get rid of this last term, which is troublesome to integrate. And how did we get to this equation? That is given is in Ito calculus, on how we got this long equation, on why we can write dv as this equation. So that is given in Ito calculus. So this is how we moved with the geometrical Brownian motion and tried to find out a solution for an equation that otherwise we were stuck at.